Welcome to The Explainer. Today, we are tackling one of the absolute most stubborn roadblocks in artificial intelligence, the memory limit. We're going to explore a really fascinating framework called Recursion of Thought, and we'll see exactly how it pushes AI reasoning far, far beyond its standard boundaries.
So picture this, because it's a situation a lot of us know all too well. Have you ever fed an AI a deeply complex problem, maybe some massive logic puzzle, only to watch it completely lose the thread and develop the memory of a goldfish? It's relatable, right? And it's incredibly frustrating. You hit this dreaded memory wall and your chatbot just stops making sense. Well, today we are unpacking exactly why that happens and, more importantly, how to fix it.
Look, the data proves this memory wall is a very real limitation. Even the absolute titans of the AI world have strict context boundaries. For instance, GPT-4o caps out at 128,000 tokens. GPT 3.5 Turbo stops at just 16,385, and Gemini 1.0 is sitting right at 32,000 tokens. The moment you exceed those numbers, the model just fails to process the information. It's game over. So, here is our game plan for today. 1. The context limit problem. 2. The divide and conquer solution. 3. How recursion works. 4. Big wins and results. And finally, 5. The catch, RoT limitations.
All right, let's jump into part 1. The context limit problem. Hitting the memory wall.
Here is the core issue we're dealing with. With traditional chain of thought prompting, as a problem gets harder and more complex, the context length just grows exponentially until it completely exceeds the maximum allowed limit. It basically forces the AI to hold every single step in its head, all at the same time. Recursion of thought, however, completely bypasses this exponential growth. It literally snips the problem into bite-sized, manageable pieces.
Which brings us nicely to part 2, the divide and conquer solution. Think of recursion of thought, or RoT, like a relay race. It's an inference framework built entirely around a divide and conquer strategy. Instead of forcing one port runner to complete a grueling marathon carrying all the data at once, it breaks a massive problem down into smaller sub-problems. It solves those in completely separate, isolated contexts, and then just passes the baton to aggregate the final answer. It is honestly a brilliant shift in how we handle data.
And just to put the sheer scale of this into perspective, 100,000. This entire framework was built from the ground up with the ambitious goal of supporting context lengths far greater than 100,000 tokens. That's unlocking a level of massive problem solving that standard reasoning simply cannot touch.
Okay, part 3. Let's look under the hood at how recursion actually works.
To actually pull this off and maintain recursive control, RoT relies on 3 highly specific checkpoints: go, think, and stop. The AI uses these special tokens as signals. It tells the model exactly where it is in the problem-solving loop during inference.
Let's walk through that loop really quick. Here's the exact step-by-step process. Step 1. The AI drops a go token to mark the start of the sequence. Step 2. When it gets stuck and needs to break things down, it produces a think token, creates a simpler subproblem, and solves just that piece. Step 3. It plugs that mini-solution right back into the main problem sequence. It just keeps looping this until the whole thing is solved, which leads to Step 4, outputting the final answer and dropping that stop token.
Moving right along to part 4, big wins and results. Let's see this in action.
When they put this to the test, the results were mind-blowing. Models using recursion of thought are hitting perfect or near-perfect scores on ridiculously complex operations. I mean, we're talking 48-digit addition and subtraction and 16-digit multiplication and division. It absolutely crushes heavy computer science challenges too. Things like finding the longest common subsequence, solving the 0-1 knapsack problem, and matrix chain multiplication. Standard methods just hit a wall with these, but RoT handles these incredibly demanding tasks flawlessly.
And here is why this is such a massive game changer for hardware constraints. Think about an older model, like GPT-3. If you give it those giant math problems using standard chain of thought, it hits a 2048 token limit and immediately fails. But if you take that exact same GPT-3 model and train it with the RoT framework, it suddenly achieves near-perfect accuracy on 48-digit math. It proves you don't necessarily need the shiny new, expensive model. Sometimes you just need to upgrade how the old one thinks.
But let's keep it completely real and move to part 5, the catch, RoT limitations. So what's the catch, right? Why isn't everyone doing this today? Well, there are a few major trade-offs. First off, unlike just typing a clever text prompt, RoT requires serious upfront investment.
You have to do supervised training on a labeled dataset before you can even use it. Second, because it's built for these massive, complex tasks, using it for everyday common questions is just total overkill. And third, and this is a big one, it can't automatically generalize length. Meaning, if you train the model to do 8-digit math, it's not going to magically know how to do 16-digit math. You literally have to retrain it for the longer problems.
To quote the source material directly here, RoT requires supervised training before you can use it to run inference. This can be a costly and time-consuming procedure. So yeah, you can't just flip a switch or type a magic phrase to make your language model think recursively out of the box. You absolutely have to put in the time, data, and resources to train it first.
So I'm going to leave you with this final provocative thought to wrap up our explainer today. Given those heavy setup costs and the need for supervised training, could this framework actually be the ultimate cheat code? Could training smaller, older models to think recursively be the key to beating massive, ridiculously expensive language models? If we can upgrade a basic AI to hit perfect scores on the absolute hardest tasks, it might just completely redefine how we scale AI in the future. Thank you so much for diving into this fascinating topic with me, and keep exploring.